Welcome to the last session of the day for the science track. I'm Adam emceeing, and we've got Charles doing the timings. We've got 3 talks for our last session. First up, we've got Emily Massahud, who's going to talk on from minutes to seconds capillary auto alignment with Python and opencv. She's a software engineer with Ansto. So I'll let you get into it.
Thank you. Working? Yeah. Hi, everyone. Today, I'm here to talk to you about some automation work I did over at the Synchrotron. I used Python, and I used opencv. But first, let's take a step back. Why and for whom? If you're here earlier, you will have heard a version of this. Mel has done a talk also about the Australian Synchrotron. For those who weren't, you're here for the first time. The Australian Synchrotron is a government research facility. We're part of Ansto, and we're just over there in Clayton, right next to Massahud. In a synchrotron, what we do is we accelerate electrons very fast in order to produce beams of light. Usually, it's X-rays. And what do we do with these X-rays? We use them to look at a bunch of different samples with instruments that we call beamlines. We have people from all over Australia, all over the world, really, coming to do a bunch of cool stuff with us. So there's like food science, there is environmental applications, energy, defense, cultural heritage. It's a bunch of cool stuff being done there. We have the advantage of producing data with more accuracy, quality, and we can do things much faster than if you do it in a normal lab. So a lot of people want to come and do research with us. Every year we receive about 5,000, actually more than 5,000 people to use our beamlines, our instruments, and over the course of history of synchrotron, over 3,000 publications have come through peer-reviewed journals of work that has been done at the synchrotron. For the past 2 years, I have been part of a team that is building a new instrument, building a new beamline. Beamlines are very complex instruments, but I'm going to show you 3 main components that will be important for our talk today. First one, X-rays, light source. Second one, where the sample is, so the sample stages. And the detector. Detector is a camera, but it's a camera that sees X-rays and not visible light. So X-ray goes through the sample, hits it, interacts with it, and then whatever comes after is detected by the detector. This beamline that I'm helping put together, it's going to do a type of experiment that's called X-ray diffraction. For that, you have to put your samples in a capillary. Think of a straw, but made of glass, and only 1 millimeter thin. That's what the capillary looks like, and you put a very, very fine powder inside. After you do that, you put that in a stage, much like this one, and you need to have it constantly rotating in front of the X-ray all the time while you do your experiment. You need this rotation to be very aligned because the X-ray path is coming through, and as it rotates, here's what cannot happen. This is a misaligned capillary. So if it rotates all the time, if it comes off of the X-ray path, you're not going to acquire quality data. We have to align this capillary. Back in the olden days, people used to do that manually. So basically, the stage has manual knobs. You go, you tweak them, so you untilt, you move it a little bit until you see that it's rotating completely aligned to the rotation axis. Although this is not easy to do, it takes time to learn how to do it. Also, it takes a couple minutes per sample. And like I said, the synchrotron needs to do things fast. And people come to the synchrotron with like 50 capillaries they want to analyze. So it would be a pain to do each one of them by hand. But we don't have to do it by hand. We have Python, and we have motors. So I say, let's automate it. This is the setup that I had. So it is a camera, a backlight, just to give a good contrast of the image that you'd see, and then the capillary sample that's mounted on this motorized stage. This is the stage. This stage has 5 axes of movement, so it moves around in X, in Z, it tilts in X, it tilts in Z, and it rotates around its axis. My task was, look at this capillary with a camera, see if it's badly aligned, and then you use these 5 motors to put it in place and ensure that it's rotating perfectly. Okay, I have motors. How do I talk to them? Our facility has this motion control system that's called EPIX. EPIX is something that's been around since the early 1990s, and it's used in telescopes, fusion reactors, synchrotrons, other particle accelerators. And EPIX is a way that your motor gets a name. So let's say I have motor X. It's called beamline motor 1 X dot value. EPIX gave it a name. If I want to tell this motor, OK, please go to position 5. You say CA put, the name of that motor, and the position you want it to go. If you want to check whether it's in the place you want, you do CA get, the name of the motor, and it'll output the current position of that motor. And you can do all of that from the command line, by the way. Now we need a way to get EPIX to talk to Python. And we do that with 2 cool open source packages called OFID and Blue Sky. Basically, OFID is a library that allows you to put your motor names with their EPIX names that they have in a Python class, and all of the components that they have will be the specific motors for that stage. While Blue Sky grabs the instances of those classes, and then it does stuff to it in what they call Blue Sky plans. So they have a simple move plan that I just grabbed from their library, and I told the rotation motor of my stage to go to position 0. As soon as I run this, my motor is going to rotate until it reaches 0 degrees, and that's it. That's all we have to do to interact with the motors via Python. These 2 libraries, they've been developed by another synchrotron over in the US, and they are used in a bunch of other synchrotrons around the world. OK, so that was the tools to talk with the hardware, but now we need the logic to make it happen. And yes, that will involve math. I'm sorry if you don't like it. The first thing I had to do was to give myself a way to visualize what was coming out of the camera feed. And that's the first time that I had to use opencv in this project. For those who don't know, opencv is a very powerful tool. It's also an open source project, and it's very powerful in computer vision and image processing in general. It is built mostly in C++, but it has a Python wrapper to it, which is very lucky for us. So I put together this little script. I don't know if you can read it well. It is quite short. There's nothing much to it, and that's why I wanted to show. It's a while loop. I am grabbing frames from the OFID device. So if I do get to the image that comes out of the device, I can get a live feed of what the camera is outputting for me. And then I put that in a while loop. I just play around with the size of this data, the shape of this data, and I use opencv's image show to continuously consume the frames, and that gave me a live feed. And that was it. That's what it looks like. This is stationary, but if I move the motor, I would see the capillary moving in real time now. That was super easy, and that was like super, super helpful as a debugging tool, because that was my eyes during the project. I had eyes, but now the computer doesn't have eyes, but it needed a way to see the capillary and a way to make decisions on what to do to align this capillary. So what the strategy that we came up with was, okay, let's think of this capillary as a line segment that goes through like the center of this capillary, and the important things we need to know about this line segment is its slope and its intercept in the image, at the bottom of the image. That's how we're going to think of this capillary from now on. And I thought, opencv again. It's going to help me. It's going to be quick. I'm going to do this in no time. But I was wrong. So my idea was to just get the edges of the capillary using Kenny from opencv, and then use half lines to get the slope of these. And then if I got the average of all these slopes, I would get a nice line at the middle of the capillary. But I didn't. The capillary is something provided by the users that come to use our facility, and they can look like anything. I was expecting a nice black solid thing. This is a purposefully bad capillary that I used, because this has to work in the worst case scenario, right? So the edges that we ended up getting for capillaries that were not completely filled, it was bad. So when you try to fit half lines, so when you try to find half lines from this Kenny, from these edges, you end up with a bunch of lines, many, many more lines. I was expecting one for each edge of the capillary. I ended up with like 20, and they all had different slopes because they were picking up on artifacts from the image. So that was a problem, and because we don't know what kind of capillary is going to come through the facility, I had two options. I could try and sample as many capillaries as I wanted to try and make this algorithm work for different types of capillary, but then I'm like, no, I did this to help me. I wanted two simple methods that would get me my line, and that's just going to be so much more work than it was worth. So I ended up not doing this. And what I did instead, I still use opencv, by the way, but I used it to just give me a binary image. So I just applied some Gaussian blurring, and then I did some thresholding. So it's ones and zeros now. Now I have a binary array that it tells me, here is capillary, or here is not capillary, with ones and zeros. And that's so much easier for me to work on from now on. Because if I look at this binary array row by row, I'm going to look at where the capillary starts, where the capillary ends, which will be where the black starts and ends. And then I'm going to find the middle of that for all of the rows. And then I'm going to have a midpoint throughout the capillary. That's what I did with NumPy. So if you see the red lines, they're actually points, but because there's so many of them, it looks like a continuous line. For each row of this array, I got start, end of the capillary, calculated the blue dots, which is the midpoint of this capillary. That was not a straight line. So again, NumPy, I use NumPy's polyfit, which basically allows you to fit a polynomial to a set of data points. I said, first degree polynomial, please. And that's basically a linear regression. The advantage of this is that even if my capillary was really, 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 really bad, I was able to get a start, an end, and a midpoint. And because linear regression, if I have one of the points very far off, it's just might skew things a little bit, and I took care of that with some statistics. But the idea is that the slope of this line will be pretty good if I do a linear regression. And it worked. With that, I could get slope and intercept. And from now on, that's how we think of the capillary. A capillary is a slope and an intercept in my image. And that worked, and that was helpful. Okay, I have eyes. The computer has eyes. So now we have to coordinate how we move the motors in the stage with what the camera is giving me as an output for how the capillary is moving. If I move left, what happens to the capillary? If I move right, if I tilt this way or that way, what happens? Here starts the math journey. So the first thing that I had to do was understand what was the orientation of the stage in what the camera plane would see. So basically, my goal was to make sure that the x-axis of my stage was aligned to my camera view. Because if I had that, if I move Z, the capillary would just be moving back and forth, and I would see no displacement in the camera. So the capillary would stay stationary in the image because it's just moving in depth. And if I moved in X, then I would know that it was a faithful representation of what the X movement looked like, motor versus camera image. And to find that out, there's trigonometry and some math. So if you find that theta angle, you'll find out how much you have to rotate that by, and then you'll have this x-axis aligned to your plane. And how did I do that? Blue sky. So that's when I wrote my first blue sky plan. So a blue sky plan is a generator, and it's a generator that you can put a bunch of small chunks of other plans into, so it doesn't get crowded, because we're talking here about doing a bunch of calculations, getting a bunch of slopes, intercepts, moving motors here, there, etc., and so on. And if you just use the syntax yield from, you can do different parts of this alignment and have a single calibration that's still wrapped up and concise. So I ran this on a Jupyter Notebook. You see that the syntax here is quite simple. I just say, I just tell the blue sky plan to please run. So if I run that on Jupyter Notebook, what's going to happen is it's going to give me a bunch of print statements. By the way, this was another debugging tool. Print everything. Just let me know anything that's going on, every motor that is moving, what calculation you're doing, what do you see right now? The computer let me know. And that was, by the way, another important debugging tool for me. I would see, okay, it's moving these many pixels, it's twisting in this direction, and so on. And this even had a way of knowing, okay, I finished doing this alignment, did it work? If it didn't work, it's going to run it again, which is what happens. And at the end, we see that the rotation is about 110 degrees. So if we grab that stage, rotate it by 110 degrees, now we're aligned the x-axis to what we see in the camera. Good. We had to do a few more of these calibrations before we were ready to run the main alignment plan. And yes, a bunch of them involve math in them. This was a cool one because this specific thing allowed me to bring down, we were having around 30 seconds of alignment to 5 seconds. So what this did is, if I find the point O in my image, which is where the tilt axis of my capillary is in relation to the bottom of the image, then I can know, once I untilt my image, I'll know this distance BC, so how much it'll have moved by, and then I need to only calculate AB, which is how much I'm going to offset it by, and then my capillary will be in its axis of rotation, which is the point A. I did this because if I measure this once, then if I take a snapshot of my capillary, I know I can move all of the motors at the same time. I have a value for how much I have to offset. I have a value for how much I have to untilt, and that can be done so much faster. Okay. This one was a bit of a nightmare because I finished my plan, I untilted, I offset. It looks straight. It's straight. It looks straight. The plan, the blue sky plan said it was straight. But then I rotate it to make sure it's straight. And it's not straight. And then I added Python code. I doubted whether I knew opencv. I doubted if the motor was giving me the right place. Is that 1 degree? It's not 1 degree. You're lying. I doubted so many things. I debugged for a long time. Print statements, matplotlib plots with slopes, intercepts, nothing. I couldn't find out what was happening. And then, one day I was not doing this, I was doing something else. I met one of our scientists, and I briefly mentioned that. He asked, how's it going? I said, oh, I have a problem. I can't figure out what's happening. And then he looked at me, he said, huh. And this person, he's got like 20 years in the facility, so I'm pretty sure he's seen it all. He looked at me and he said, I've seen this before, Emily. You know what it is? The camera's crooked. Look at this. Tell me if that's not what's happening. The camera is placed manually on the stage. And it's very well placed because this crookedness that I found was of like 0.8 of a degree. It's very good for manual placing, but it was not 0. So of course, we would see a difference in a capillary that's 1 millimeter thin. Fortunately, I was able to fix that, and I was able to factor that into the code. And we can align the capillary now. So again, another blue sky plan. This one is just going to home the stage, bring all of the motors to position 0, and then I'm going to use the OFID device to continuously rotate, just to show you that it is not aligned. It's even nodding, no, it's not aligned. And then it's just going to run the alignment plan. So I just have this run. Ready? Done. And now you see that all the motors only took 1.7 seconds to move. And if I rotate this again, ta-da, it's aligned. So it was a lot of tears, sweat, craziness, talking to other people. But finally, we did it, and it's 5 seconds. Done. Few things I learned doing this. Facility has 150 people. We have scientists, we have mechanical engineers, electrical engineers, controls engineers, scientific computing. We have it all. Physicists, chemists, biologists. Yes, I needed them all. Without them, I wouldn't have finished all of this. I was silly. I printed everything. I printed, okay, I am moving this motor by this much for this reason, because I needed to know what the computer was doing at all times so my brain could understand what it was doing, and then if a problem came around, I knew how to fix it. And I did it all with open source code. So opencv, Blue Sky, OFID, NumPy, Matplotlib, all these tools, open source, and they were enough and math for me to finish quite a complicated project. Here, I just wanted to thank a few people. First one is the scientist for the beamline that we're building, so Dr. Josie. She was my go-to. She was the person I cried to, asked for help in math and in logic and everything. And of course, the scientific computing team, which helped me with code, helped me with pull requests for the length of the 6 months that I was doing this project. Thank you, PyCon, for having me.
All right. Thanks, Emily. That was an awesome talk. Very great story. It's good. Any questions from the audience? We've got time for 1 or 2.
It was a great solution and that you got there in the end. Is the camera mounted on some kind of staging thing that can also be software controlled, and is that how you fixed it? Or...
No, I didn't move the camera. I calculated what was the tilt, and I factored that in to my code. So I knew that if my capillary was placed at a 0.4 degree, it was aligned. If I can't move hardware, I'll fix it in software.
Any more questions?
That camera, was that hard-coded, the tilt, or does it change and you have to recalibrate?
If you bump it, let's say someone is mounting a new sample, they bump the camera, that changes. So you have to recalibrate in the future.
Yeah, good.
And one more.
Yeah, just a question. Did the system have any awareness of where the X-ray beam was going to be? Like, did it get it in the right position, or?
That is not factored in this part of the code, because below this stage that I was moving with 5 axes of movement, there's another stage that moves in X and Y and Z, because our Y is height. So that is done with a different type of calibration, and it is related to Mel's talk from this morning about commissioning tools. It's kind of, we have to wait until we have X-rays, and then we move this stage below, and then we see where's the place where we can align this whole chunk of thing to the X-ray.
Right, okay, thank you.
Awesome. We might call it there. Thanks heaps, Emily. I'd like to everyone join me in thanking Emily, and we'll come back in